In this video, we are going to discuss about atmospheric pressure. What is the pressure exerted by atmosphere? And we'll see a device which will be used to measure this atmospheric pressure, that is called barometer. Right? It's a very nice device and very innovative method of measuring atmospheric pressure. Right? See, we have a Earth, and above the Earth, or this is Earth, say radius r, and above this Earth, outside this Earth, you have atmosphere. You have the atmosphere, right? You have gaseous particle, atmosphere, till the height of say approximately 200 kilometers, till the height of 200 kilometers, right? So we have say atmosphere approximately up till the height of 200 kilometers, right? So here we have gases, right? We have the molecules, oxygen, nitrogen, little bit of carbon dioxide, and some other gases also. So you have some density also, and at the highest point of the atmosphere, I can take pressure to be, say, call it point A. At this highest point, the pressure is 0, because you don't have anything beyond this to apply any force at this point. You don't have anything beyond this to apply any force at this point, so the pressure is 0. But as you go down from this point, if I talk about this point, say this is point, say X, and suppose X is at a height, say distance Z below the upper layer of the atmosphere. This point X is lying, say Z1, at Z1 below the upper layer of atmosphere. Then pressure at X will be given by rho. See, you have this formula. dP is, as you go down from this point, the pressure changes by this magnitude. If I go below by dz height, so pressure will increase by rho g dz. So dP, if z is the reference of measuring z is this layer, so take it, this is taken as z equal to 0 to z1, and this is pressure over here, is pressure at this point, say I call it A, and this is B. Then pressure at A and pressure at B. At A, what is the z value? 0. At B, z value is z1, right? So you can say PB minus PA is rho g dz, 0 to z1, and PA is 0. So pressure at any point B, z1 below the upper layer, is going to be this integral 0 to z1. And I can't take rho outside or g outside, because for the variation of say 200 kilometers, I cannot take g everywhere constant. G will depend on the height. G will vary from one point to the other point, as we are talking about wide variation in the height. And rho is also changing. The density of air in the atmosphere is not same at every height. So but I don't know how the rho is changing or how g is changing, so I can write simply like this only. P at any point X is going to be rho g dz from 0 to z1, where X is lying at a distance z1 below the upper layer of the atmosphere. So if I want pressure on the just above the earth's surface. Then pressure just above the earth's surface, which we call atmospheric pressure. Pressure just above the earth's surface is going to be rho g dz, 0 to the total height h. This is the total height h of the atmosphere, right? 200 kilometers, 0 to h, right? So that's the pressure, that's the atmospheric pressure. The best way to measure it is, you take a small surface delta s, you take a small surface delta s and see what force is acting on it, and then pressure P atm can be simply calculated by F upon delta s, where delta s is very small. That's the way to calculate P atm. That's the way to calculate P atm. This delta s may not be horizontal, it can be like this also, no issue. In that case, force will act in this direction. See, force due to atmospheric pressure, always, force due to any pressure acts always perpendicular to the surface. Acts always perpendicular to the surface. So the surface need not be like this. It can be anything. It can be like this also. It can be like this also. You can take like this also. And then force will be in this direction. So F by delta S tending to 0. That will give you P atm. That's going to give you P atm. This is how P atm is defined. This is how P atm is defined. And we can write like this also. But then this Torricelli, he was a very great physicist who had a lot of contribution in fluid dynamics. He designed a very innovative device to measure this atmospheric pressure, and which he called barometer. He called it barometer, right? Torricelli devised a apparatus, a setup that's called barometer, to calculate this atmospheric pressure very easily, very easily. See how we can calculate it. See how we can calculate atmospheric pressure using barometer. And what's the principle of barometer? What is the principle of the barometer? I'll discuss with you. See, he took a basically glass tube. He took a glass tube. I'll draw that glass tube for you. Say this is the glass tube. Say having height 1 meter. Having height 1 meter, say. He took a glass tube, and glass tube is like this. And into this filled mercury. He filled mercury into this. The whole 1 meter of glass tube is filled with mercury. He filled mercury into it, and then he temporarily closed this. You can close it using thumb also, any temporary way of closing it. He closed this temporarily. You can use thumb also to close this. And then what he did was, he took a cup of mercury. He took a cup, and cup was filled with mercury. And by closing this, he put it upside down, and he put it upside down, and it went like this. See, when you put it upside down, how will it look like? It will look like this. You had a cup of mercury. You can completely immerse it also, or you can simply put it like this also. This may not be very large. You can even take a tube of height more than 1 meter. It's better to take sufficient height. And you just invert it in this cup. You just invert it in this cup, right? invert it in this cup. So you'll find that once you invert it in this cup of mercury, once you invert it in cup of the mercury, see what will happen. This mercury will come down a little if the tube has got sufficient length. This part of the tube should be having height around 1 meter. This should have a height around 1 meter. It should be at least greater than 76 centimeter. The height of this uppermost portion of the tube above this mercury surface in the cup, this height must be more than 76 centimeter. Only then this will work, right? So if height is enough, we usually take it as 1 meter. In that case, you will find that if it is say 1 meter, if say it is 1 meter, then some portion of the tube will get empty. Some portion of the tube will get empty. And remember, see, we put this upside down, temporarily closing this part. So you put it upside down and then you remove the closer. You don't, you remove your thumb from here. You put your thumb over here and you put it upside down and then you remove the thumb. The moment you remove the thumb, the height of mercury will go down. There will be some empty space created over here. Once you remove the thumb, the mercury will flow and there will be some empty space created over here. And while we do this, we do not allow any air to pass into this tube. So this is vacuum. This is vacuum. So I can take pressure over here is P0 to be 0 over here. Vacuum, so pressure is 0. So I'm interested in finding pressure over here. See, this is atmospheric pressure. I'm interested in finding pressure over here. And pressure over here is same as pressure over here. Pressure over here is same as pressure over here because height of A and height of B is same. And we know the pressure at this point, C. Pressure at this point is 0. So PB is what? PC plus, if suppose this height is say Y. Y is the height of mercury above the upper surface of the mercury in the cup. This is cup. This is cup. So suppose Y is the height, then we can say PB equals to PC plus rho gy, and PC is 0 because at C you have vacuum only, so it is rho gy. So pressure is rho gy, and this Y has been found to be, in this case, 76 centimeter. Y has been found to be 76 centimeter. So sometimes pressure, atmospheric pressure, is also measured on the surface of the earth. This Y has been found to be 76 centimeter, normal atmospheric pressure. So sometimes pressure, atmospheric pressure, is also measured in terms of height of the mercury above this A. Sometimes the unit, the pressure is also expressed. You can say pressure PATM is rho gy, whereas the Y is the height of this mercury above this A. So sometimes we also express atmospheric pressure in terms of Y. So if suppose Y is 76 centimeter, so 76 centimeter of mercury, height of 76 centimeter of mercury, correspond to how much pressure? See, rho is what? Rho is, see, specific gravity of mercury is 13.6. 13.6 means what? Specific gravity 13.6 means rho of mercury is 13.6 times rho of water. Rho of water is what? 1 gram per centimeter cube. So if I put it in terms of kilogram meter cube, so it is 1 10 to the power minus 3 kg, and 1 centimeter cube is minus 6 meter cube. So that comes to be 10 to the power 3 kg per meter cube. So rho hg is 13.6. See, this is called specific gravity. So specific gravity of 13.6 means the density of mercury is 13.6 times density of water, and density of water has been taken to be 1 gram per centimeter cube. So this is the density of mercury. So that comes to be 13.6 into 10 to the power minus 10 to the power 3, and G is say 9.8 and Y is 76, so 0.76 meter. And if I evaluate this, it comes out to be 1.01 into 10 to the power 5 Newton per meter square, and this is called also Pascal. This Newton per meter square is also called Pascal. That's the SI unit of your atmosphere, any pressure. Pascal. 1.01 into 10 to the power 5 Pascal. Right. So this is how barometer works. This apparatus is called barometer. This apparatus is called barometer. We call it barometer. So atmospheric pressure in general is taken to be 1.01 into 10 to the power 5 Pascal, which is a great, which is very high amount of pressure. See, 1.01 into 10 to the power 5 Newton per meter square means what? If I have the area of say 1 meter square, if I have an area of this 1 meter square, then on this area you have a force of 1.01 into 10 to the power 5 Newton acting on this. If I have area of 1 meter square, then this amount of force is acting, and this is great force. This is equivalent to as if you have kept on this 1 meter square a mass of a body of mass 1.01 into 10 to the power 4 kg of weight, as if somebody has put say 1000 kg of mass over here. So this is huge weight, right? If somebody is standing, say if I am standing on the earth's surface like this, our head, what would be the area of our head? Cross section area of our head. Cross section area of our head will be how much? What's the radius of the head? What's the diameter of the head? Diameter of head can be, if I measure, it could be say the cross section diameter can be 20 centimeter. So the area will be of what range? 20 into 20, it is 400 centimeters square, right? Or if I talk in terms of meter, this is 0.2 meter, so 0.05 meter square. So the force acting on your head due to atmospheric pressure would be how much? 1.01 10 to the power 5 into this area 0.04, that is 4 into 10 to the power 3 kg. So that means you are lifting 4000 kg on your head. Atmospheric pressure, it is as if the equivalence, we can draw an equivalence, you are lifting 4000 kg on your head, which will be equivalent to as if you are lifting 2 elephants on your head. Every time you are lifting 2 elephants on your head, the amount of atmospheric pressure is putting a force on your head that is equivalent to weight of 2 elephants, 2 small elephants. So you can understand the magnitude of atmospheric pressure which you have, or the force which is generated by atmospheric pressure, right? But we don't feel it because we are lifting this 2 elephant since our childhood, so we don't have a feel of it. We don't have a feel of it since we are lifting it from our childhood, right? Okay, fine. Anything else? Yes, one more thing. I'll also talk about a device which is used to measure pressure of gases in a vessel. How do you measure pressure of gas in a vessel? If you have a vessel, closed container containing a gas inside, so how do you measure pressure of that gas inside vessel? So let's try to see how we can measure it. We have a device called manometer for this purpose. We have a device called manometer for this purpose, and I'll tell you how this device works, right? Suppose we have a container. So this is a container containing gases, right? This is a container containing some gases, and let's make a suppose it contains gas and we want to measure the pressure of the gas inside. This is containing a gas and we want to calculate the pressure which you have in this gas. So what we do is, so we connect a tube over here, we make a hole and we connect a tube over here. It is this kind of tube. You connect a tube like this. Sorry. We connect this kind of tube, the U tube, and we fill some liquid, right? We fill the liquid in this U tube. So you'll find that there is a difference in the height of liquid on both limb of the tube. You'll find difference in the height. Say, let this point is A. So pressure at A is equal to pressure of gas. So pressure at A is equal to, say, take point B over here. Pressure at A is equal to pressure at B, since they are at the same height. So pressure of A is equal to pressure of B. And let this be point C. So pressure at C is what? Pressure at C is P atm, since C is in contact with the atmospheric pressure. And suppose this is height H. H is the difference in the height of the liquid in both the branch of the tube. This is U tube. So H is the difference in height of the liquid in both the limb of the tube. Over here it is some height, here is some height. H is the difference in the height. So PB is what? PB is PC plus rho GH, and PC is what? PC is P atm, right? So pressure at point B is same as pressure at point A, and is same as pressure in the gas. So pressure in the gas will be P atm plus rho GH. And this difference is called, this difference in the Pg minus P atm, which is rho GH, that's called gauge pressure. That's called gauge pressure. Alright, this is called gauge pressure. Getting your point? So that's how manometer works. This is called manometer. This is called manometer.